KI4IO, and this presentation is going to be about making an antenna coupler. The antenna coupler that we're going to be talking about is the one just above my head with the funny little, all the wires sticking out of the front panel. Give you a quick tour of the station. On the bottom left is a homebrew 40-meter direct conversion transceiver. I talked about that a couple years ago. To the right is a 30-meter super het transceiver. Above that is a 20-meter transceiver, and then my K2. Two tuners piqued my interest in as far as these antenna couplers. The first one was a tuner built by Zach Lau. It appeared in the 1990 ARRL antenna book. The second one was the antenna coupler built by Dean Stroff, and I first saw it in the 2015 article entitled "Don't Blow Up Your Balun." Both of these couplers were unbalanced couplers and had baluns on the transmitter side of the coupler, as opposed most antenna couplers we see have it on the antenna side. As the convention is, I'm going to use transmitter side and antenna side, because sometimes when we talk about antenna couplers in terms of input and output, I get a little confused. Also, both of these couplers, both Zach Lau's and Dean Straw's, were floating from ground. I have to toss out a modest limerick here at the start. In days of old, when hams were bold and baluns weren't invented, we adjusted our C and fiddled with L, and reflected power was prevented. The baluns, the subject of baluns has gotten to be so complicated anymore. There's a recent QRP ARCI talk. Somebody tossed out an innocent question about a Carolina Wyndham, and the post finally stopped at 74 posts. Most of it was arguing about baluns. Just amazing. In the 1950 antenna book, you can find like 2 paragraphs about baluns. Now that's all we can talk about. Some technical terms. This is the Dewey decibel system. This loose parts. Dave Blazek must be one of the funniest cartoonists going. This was in the Washington Post. Here's Zach Lau's tuner. The schematic is a little convoluted because he was doing all kinds of things. He did 2 things here. He had a tapped inductor, and he had his shunt element was a capacitor, and he could move the capacitor to either the input or the output of the thing. And that would make it either to work on either high or low impedances. And then his balun, as you can see here, was on the transmitter side. And this one was the tuner from Zach Lau. I'm sorry, I misspoke, Dean Straw. And Dean Straw is retired from the ARRL. And this tuner was a beast. It was a 1 kilowatt high pass T network with a choke balun on the antenna, the transmitter side. And this was also floating from ground, but put in a shielded box. To talk a little bit about my antenna. My antenna is a 65-foot flat top fed with homemade open wire line. Spacers are just plastic scrap, and the wire is number 14 insulated wire from the hardware store. And I think this is just a wonderful, wonderful feed lines. Before I go any further, I got to tell you that Dean Straw's article, "Don't Blow Up Your Balun," may be the best 7 pages ever written on the subject of antenna tuners and whatnot. It's in the June 2015 QST, pages 30 through 36. And if you're an ARRL member, you can go back in the digital archives and pull this thing up. I actually cut it out of mine with a razor blade and scanned it into my computer so I could refer to it on occasion. What a beautifully written article, which talks about baluns and transmission lines and more appropriately loss in antenna tuners and matching systems. So there's a big argument about whether balun should be on the transmitter side or the antenna side. And I've never seen such fervor among the proponents of the antenna side, rather. They get into big arguments. When you tell people you're going to make a coupler with a balun on the transmitter side, it's like calling them names. Tuners like this must be isolated from ground. And so wonderful talk. I think it was Joel Hollis from the ARRL, the doctor is in, talked about a huge toroid that can be slid over the antenna coupler. It should make no difference whether the toroid is on the antenna side or the ATU side. Here's a little sketch that I made to try to show that. The rationale for a balun on the heating, the antenna side, an argument is made that the balun will be subject to heating. And for sure, that's true. I mean, when you have open wire antenna systems, you can get some pretty high SWRs. I mean, it would not be uncommon to have SWRs of 20 to 1 or maybe even higher on an open wire system. It's also claimed that a balun on the transmitter side will then be operating at its design impedance. In other words, at that point, you've transformed the impedance down to 50 ohms. So, but let the fight go on. Go out on the internet and pose this one and see what people say. Speaking of baluns, I had mentioned this earlier. The furor over baluns. There's QRZ.com. There's an antenna thing in there, and I think most of the people weighing in and asking questions and being yelled at and scolded and whatnot, it's mostly all about baluns. W70L wrote a beautiful paper on baluns, what they do and how they do it. I stole his drawing. If you're out there, Roy, thank you. I owe you a beer. But this is basically what the issue is. We have a balanced transmission line, and we have an unbalanced rig, and this is sort of what the balun does. It takes you from that balanced feed to an unbalanced, in this case, source. And here's what I love about the balun fight. So years ago, Halley's Comet was visiting Earth. I think it was 1976. And you're probably wondering what Halley's Comet has to do with antenna couplers. Well, there was a big brouhaha in the astrophysics community. It's tumbling about the long axis. No, it's tumbling about the short axis. Well, as it turns out, both sides were right. And that's the way it is with some of these arguments. Here's the deal. You're wrong, I'm right. I'm right, you're wrong. We're both wrong, we're both right. And so it is with baluns. There's more than a few ways to skin a cat with baluns. And I think you just have to keep that in mind when you begin winding these things. I've made several varieties, and I'm not seeing a lot of difference, at least in the bands that I've been operating on. So it is with baluns. Remember, you can both be right. I built Dean Strauss coupler. I didn't exactly replicate his design. And then I began to make some measurements. So his was built on what he called a common substrate, and the common substrate I used was a metal plate. The front panel of this thing was a piece of, it looked like Bakelite, but I've bought some Bakelite since then, and it didn't look like that, but it was a very hard material like Bakelite. And I began to make measurements. The measurement that I began really thinking about was the balance measurement. In other words, your coupler, if you're going to be feeding a balanced antenna system, you need to be shoving energy out into that two-wire line in equal and opposite in phase. The imbalance can be compensated. I hooked this test up to Dean Strauss coupler, and the balance was awful. I could not ever figure out exactly why. I thought the balance could be compensated for. I couldn't figure out how to do it. So the issue of a balance in the feed line is pretty important. An unbalanced feed line, as we know, radiates energy and distorts the pattern of your flat top antenna. An unbalanced antenna also becomes a vertical receive antenna. It picks up local noise, which we say is vertically polarized. So coupler imbalance, at least in my traditional installation, I have down here causes noise. It doesn't cause noise, it picks up noise. That's probably the better way to say this. So you have to be careful. Feed lines, antennas that have feed line as part of the antenna, maybe the Carolina Wyndham and some of these others, I'd be real cautious about using antennas like this as a noise pickup. Lloyd Butler, here's the guy who came up with a way of measuring the antenna balance, that schematic that I had earlier. So apart from distorting the radiation pattern, it encourages induction into equipment of vertically polarized noise near the field source. This is actually true, and I actually was able to prove this. This is how I measured it. Put a couple resistors in there and use a high Z probe to measure the output. Now he went through a rather extensive measurement procedure where he used a bunch of very different resistors. I think I pretty much stuck with 620 ohm. Just wanted to get a relative understanding of the antenna balance. How good should a tuner balance be? Well, it's interesting. He thought that above 80% is being tolerable and above 90% is being quite good. I found those numbers to be not good enough. I found you really needed to be in the mid 90s to be not having noise pickup, which was objectionable. So 80%, where did that come from? So I used my Johnson Matchbox, by the way, which kind of comes in at 100%. Duh, what a beautiful coupler. And I purposely unbalanced the antenna with a variable capacitor on one leg until the noise came up about 3 dB. And then I measured the balance, it was about 85%. Now this is not the most scientific test because my S meter on my K2 that I was using is a little bar graph. So was it 3 dB or 4 dB or 2 dB? I'm not sure. But at any rate, it was in the neighborhood of 3 dB noise. And it was very, 3 dB is quite a bit of noise. I measured the balance, it was 85%. You really want to have a coupler, which is much better than 85% in terms of balance. So while that Dean Straw coupler didn't work, so I decided to go to an L network, which was basically what Zach Loud did on his. And the L network coupler, if you're going to use a reversible one, you can make it with just 2 components. And you can make it either high pass or low pass. So Richard Measures, if you go Google AG6K and look at this, has a wonderful little paper on these balanced antenna couplers. By the way, he terminates his coupler in a 1-to-1 Balun on the transmitter side of the thing. And you can see that he has got 4 variations of the L networks. The L network that I selected was a high pass configuration. And here's why. I have a 22 kilowatt daytime flamethrower broadcast station, which is exactly 3 kilometers from my house. And it has caused problems. I've had problems when they've had their transmitters go amok. These places are all remotely operated now. And here recently, it was putting out all kinds of garbage into the 40-meter ham band. And I spent a lot of time yelling at the FCC to have somebody go over there. And eventually it got fixed. But so I picked the high pass configuration for this only reason. You don't have to do that. I picked the reversible L network, and I picked to have the inductor as the shunt element. If the inductor is in position A, that's for a high impedance load. And if the inductor is switched over to B for a low impedance loads, and quite low impedance too, I must say. Now here's the deal. I show a switch here. And I did build one of the couplers, one of my prototypes, with a huge ceramic switch out of one of these World War II antenna couplers. And something was amiss. It just did not seem to work very well. And I finally figured out there was just enough stray capacitance in there to bugger things up. On one of the couplers I built, I put a couple banana jack sockets back there where I could just jumper from the top of the inductor to either position A or B with a banana jack short. And finally, in the version of the coupler that I have on my operating station right now, I just have a small piece of wire with a big alligator clip on the end of it. And I just reach back there and move it from one part of the capacitor to the other. But the simpler you make this, the better things go. And some precautions. Some years ago, making antenna couplers is a lot of fun, but I burned up a couple finals in my K2 while tinkering. And so I ended up making one of these resistive bridge SWR bridges, so that when you're in the tune position, the SWR bridge is providing a pretty decent load to the K2 or whatever your transmitter is while you're tuning. Man, I tell you, if you're going to play with antenna couplers, really, this is I think it's a necessity. I think I just saw a big dummy load too on the latest QST, which uses a bunch of these resistors. But anyway, this is what the guts of the resistive bridge look like. So just to be safe, I put my shack bridge in line as well, and I have to do that the way my rig is, the way my station is currently configured. I have another bridge here, and this is also a homemade bridge, and this is by G3YNH. It's a beautifully written design bridge. Rather, it has very low insertion loss, less than 0.1 dB, They had the K2, by the way, another argument for buying a K2. The finals were $18. I don't know, try that with your new Kenwood or something like that. So in the process of arguing about where the balance should be, one of the guys from the old QRP Tech Forum, David Ryburn, who was vehemently against me putting a balun on the transmitter side, I gave him what I thought were the dimensions of my feed line and antenna system, and he sort of came up with what he thought the impedances might be in a model. I later on measured these things, and while this is not exactly what my antenna turned out to be, it shows its representation. It's good enough, and it really tells you a nice story here about open wire line. If you take a look, using a 40-meter antenna on 80 meters with 55 dB open wire feed, the loss was 2 dB. And now as you get up to where the antenna is larger in terms of wavelength, 40, 30, 20 and onwards, the losses become basically not measurable. The impedances get to be a little awkward, but the antenna losses become very, very low. This is really the lesson for open wire line, and one of the reasons that I think people really need to reconsider open wire feed. You know, a lot of the modern antenna designs we have a lot of really, really unusual designs to present a less than 3-to-1 load to a modern transmitter, which has a built-in ATU. This is sort of an old school way of doing it, and you're guaranteed it's going to work pretty well. Go back and talk about the Johnson matchbox. This is the gold standard. No matter how many times I measured this, it always come out to be exactly 100%. This picture's from the internet. It's basically the covers are off. Those of you who've owned a Johnson matchbox, you know, to take one of these apart, I think it's 40 screws, and it's an afternoon's work, and you've got to get everything all set up before you put the cover back on. I got mine for 25 bucks at a Hamfest, and it didn't work. I don't know what the heck was wrong with it. So I went through the laborious process of taking it apart. And when I did, I found out that one of the big heavily soldered wires had come adrift over the years. So I resoldered it, put it back together, and bingo, I got a great one. I want to give you a tour of some of the other couplers I've made over the years. You know, Farhan, if you're out there, what a great tuner. This is, if you go on Farhan's site and Google balanced tuner, this is my version of his antenna coupler. This is for balanced feed only. I think you can unbalance one leg and it'll work that way. This is the front panel, all these switches, which short out inductors on the rear panel. There's the tuning capacitor. What a neat coupler. I have since something happened to one of these switches, and so I'm going to rebuild this thing and use some different switches. Those switches were really hokey. And then there's VK5BR. Lloyd Butler, his if you go to Lloyd Butler's website, VK5BR, he's sort of the modern daddy of the Z-Match transmitter. And when you go back and look at that little drawing I had earlier, that he had a correction capacitor in there, that if he thought that if you got a load on the Z-Match that was not balanced, that you could put a capacitor to ground in one of the legs and fix this. And I'm going to talk about that in a bit. This is a nice little coupler. There's my version. It's not the prettiest coil that I wound there, but it works pretty good. But you can see that you really probably want to be above 90%. And I have that on 40. It works pretty good on 82, as I recall. I don't know why I didn't take a measurement of that. So, and Lloyd Butler also designed a T200 big fat toroid version of this thing too. And he suggested that the open frame coil would work better. Here's my version of a plug-in coil matchbox. I did not measure the balance of this thing because I think it could be, no matter, you could probably arrange the taps to make the balance perfect regardless of the output. So this is interesting. I had a ham buddy over to my house, George Lee Master, if you're out there, how you doing? And we hooked up my Johnson matchbox to my balanced antenna, and there was some line imbalance. And I thought, well, isn't that odd? You know, the coupler is perfect, but we have some imbalance here. Well, I went out and looked off the deck, and sure enough, one of my legs of my dipole was touching a tree branch. Well, there's various ways to incur imbalance in an antenna system. One of them is to use a poorly designed coupler. The other one was to have a tree branch. So I found a trimmer for that. There you go. So if you're of a mind and can get somebody up high enough in the tree to do that. So but Lloyd did suggest you could put a balancing capacitor. You would have to sort of experiment which leg you wanted to put that on. And I fiddled with this actually, and it works pretty nice. You can actually see the two waveforms sliding back and forth across each other. It's going to be a crapshoot as to which leg you want to put this on. And you cannot use this little balancing gymnastic thing on a coupler like my L network, because I think it only works on couplers with link windings. I tried this on my L network and it just plain didn't work. That capacitor was just in parallel with the either the inductor or the inductor and the capacitor, and that just wasn't ever going to play. But a balanced capacitor probably would work if you had a coupler with a link winding. This was pretty neat to do. It was fun to do. So after I built Dean Straw's coupler and it didn't work, I thought, okay, plan B, I'm going to make a coupler just for 4 days in May that did not use an expensive roller inductor. And the problem there is, and I have an article in QRP Quarterly about how to mimic the fidelity of a roller inductor. You know, a roller inductor is infinitely variable. I mean, you have because it's a roller inductor, but they're very expensive. And they can be dirty. I have a couple roller inductors, and one of them just sort of bounces around. I'm forever cleaning the coil, and you can buy new ones of these things they're pretty pricey at some of the ham fests. Occasionally you'll find one for 10 or 15 bucks, and if you do, go ahead and buy one. So I wanted to make an inductor with both coarse and fine tuning to try to mimic that fidelity of the coupler. First, I made the coarse tuning inductor. I did a QRP Quarterly article about making a tapped inductor. And so I made a faux roller inductor, and there the article talked about that. This was number 14 solid wire. I think there was like 22, 25 turns around a T200 yellow amidon core. And then you have to make a template. Those of you who remember your old high school, maybe you still have your protractor. You remember your protractor? I guess you can still buy one, but so you have to make a drawing of this thing and then drill the board where it goes in, and then fit these wires into the thing. It takes a little doing, but it can be done. And this was a prototype coupler that I was using, and you can see the front panel is not made for prime time. It was some kind of a cardboard on steroids. It was like a pressed cardboard or something. I don't know what this material was. I have a few more pieces of it around the house, and it's pretty nice to use, actually. Fitting the coil in there. Is fine tuning necessary? And the answer is probably yes. Any of these antenna couplers that I built above 20 meters, I really couldn't get a good match. By that, I mean really close to 1-to-1. Your mileage may vary. You might get lucky and find out that your coil taps on the gross coil are sufficient. So I tried, don't give up your day job, Jerry. Actually, I'm retired. I did give up my day job. I tried making a variometer, and this was kind of fun. This was one of the versions, and this is when I decided, man, I need a different plan. This kind of worked. And by the way, out on the internet, the internet WOG suggested the variometer is a very bad idea for an antenna coupler. I'm not so sure I agreed with that conclusion. I made tap coils. I tried brass bolts, steel bolts, switches, many turns, few turns, and this really didn't seem to be giving me the variation in inductance that I wanted. And finally, I ended up just making the baby brother of my big coil. I just used a T80 coil. I think it was a 10 position switch or 10 or 11 position switch. And I made that there. And, these switches are probably available out on the eBay and stuff like that. I had a couple in my junk box. And now, as it turns out, the fine tuned coil in conjunction with the coarse tuned coil is absolutely perfect. I can get a match on all bands. But before I did the fine-tune coil, I tried some other stuff. Here's my prototype. And I call this, it's in a file in my computer called the ugly coupler, and you can see why. The Balun over there that I used was one of those ones with a pair of windings, a transmission line winding. I later replaced that with a coax Balun. And here's the prototype. And you can see the big clip lead where I can clip onto the antenna side or the rig side of the variable capacitor to change the loads for either high impedance or low impedance. This is it. This is, I can't make the antenna coupler more complicated than this. This is a very, very nice coupler. So I made a nicer version of this coupler using a roller inductor. I have a trick quiz. You know what the answer to this is. So, but here's the quiz question: which coupler had the better balance? Well, the answer was the ugly one by a large margin. And I'm not sure I ever understood the two of them on connected to the same antenna and same frequency. The ugly coupler was vastly superior. There was no noise. The handsome coupler built on 30 meters had at least one S unit of noise. I'm not so sure I measured the balance, but it must have been in the low 80s. And I'm not sure I quite understood the reason. It may very well be that the big roller inductor, has a large electromagnetic field, and sort of maybe that was part of the reason why the balance was not so good. I don't know. All I know is that the ugly coupler won. Both had the same. Took the shielded coupler versus the open. The ugly coupler was just a very simple layout. So I built an improved version of the ugly coupler, and it wasn't as good. The ugly coupler is too ugly, so I made the nice version that used tap toroids, but I used slide switches for the tap toroids. Okay, this is pretty, isn't it? Well, guess what? If you want to be happy for the rest of your life, what do the guys say? Make an ugly woman in your life. This was a little bit too pretty. The slide switches just didn't work. The balance of this coupler was not so good. I can't remember what it was. I have it written down in a notebook somewhere. But the ugly coupler was still winning the day. The balance improved dramatically when the slide switches were removed from the circuit, but I did lose the fine tuning. So the final version, here it is right here. And this is in use right now. You can actually see that maybe over my shoulder up there on my stack of ham gear up there like that. There it is. And so to change bands on this thing is I have a little lookup table, a piece of paper. For 30 meters, I put this clip lead on number 10. I set the capacitor to number 13 and switch on number 7. And I'm pretty much ready to go. So QSY with these things is just a matter of a few seconds. Pretty nice. There's the top view. There's the little alligator clip lead to change the load impedance from the high impedance input to low impedance antenna input, right there. And that's it. I use this on 80 meters, and it works just very, very nice. 80 all the way through 10 meters. I have it all with all the bands. The final balance, this is when I started playing with baluns, with a 20-turn bifilar balun. This was a balun with bifilar wound coil, 97, 95, 90. These are pretty good numbers. Not as good as a Johnson Matchbox. And why that one on 15 meters was that way, I have no idea. I started playing around with coax, and clearly I was either using this wrong core or not enough turns or something, but I ran very good balance numbers on the lower bands. And on 20 turns of coax, I ended up with a perfect balance on 30 meters and good balance on some of the other bands. Maybe somebody who understands balance can explain these numbers. One of my conclusions was, I don't know that much about balance. The one-to-one current balun as suggested by W70L seemed to provide the most consistent results. So I thought, well, I've been arguing with people about putting a balun on the antenna side of the coupler for this entire time. But what about, I said, I'm sorry, I've been arguing about my case about putting a balun on the transmitter side of the antenna coupler. Let's put it on the antenna side of the coupler and see how it goes. So I put my one-to-one balun on the antenna side of the coupler, and I got slightly better results. But the tuning, I'm not sure I understand why this was the case. The tuning was very awkward and very critical. I found my tuning numbers, my presets were very different, and something was going on. So, but these are very good numbers. If you're gonna build this thing, try it both ways. If you're happy with the way the tuning is, I would build it with the balun on the antenna side. So the balance measurements that I did basically confirm. I mean, the difference between maybe 96%, 99% was not a whole lot of difference in balance. What about a coil balun? I just finished reading on one of the antenna forums, Zach Lau talking about this coil balun, which I made. It made pretty good balance, but it was very noisy. And so my guess is that you probably ought to avoid this. I think a coil balun at the antenna feed point, I think, is a perfectly acceptable way of doing a choke thing to keep RF off the outside of the transmission line. But I think for the purposes of making an antenna coupler and going for the balanced to an unbalanced thing, I think you probably ought to avoid this. Now the 4-to-1 balun is interesting. While I tried a couple of different 4-to-1 baluns, and I can tell you right now, I think a 4-to-1 balun on the antenna side of an antenna coupler is a bad idea. In fact, I would say on the lower bands, it's not just a bad idea; it's a supremely bad idea. So you can see that the impedances of an antenna, of my antenna, with my balun are pretty good. But when you get down to 80 meters, where the resistive component of the feed line impedance is 11 ohms, and when you use a 4-to-1 balun, you're now transforming that 80 meter impedance to 1.9 ohms with a reactance of 157 microamperes. And my apologies for not changing this to R plus or minus JX. I was just too lazy to do that. 1.9 ohms is a big ask for an antenna coupler, and I think really puts a little strain on the inductor. I would just not do this. You can see the 4-to-1 balun probably works okay on the higher bands, but I, quite frankly, if I had an antenna coupler that had a 4-to-1 balun on the front end of this thing, the antenna side, I think I'd go in and try sticking in a replacement. The coupler with a balun on the transmitter side is now in daily use and works perfectly on all bands 80 through 10 meters. And that's sort of the takeaway, but I'm not done yet. So I'm just realizing these slides aren't telling. So one of the wogs on the internet, don't you just love all the experts out there? Don't use an SWR meter, it'll steal more than half your power. And I thought to myself, really? I don't think so. So this person who said this must have been thinking about a resistive bridge. Okay, well, that's possible. So I built a fleet of SWR measuring devices. This was rather fun. And you can build some of these things in like a couple of hours. So I wanted to measure the loss of SWR bridges. Just how bad is it? So I built a whole bunch of these things. And this was really a lot of fun. First thing you got to do is build a good, make sure you got a good dummy load, and that's off on the left-hand side there. I've got, I think, a bunch of 150 ohm resistors in parallel. I think the one I liked the best was the Stockton bridge. For those of you who buy stuff from W8DIZ, I would run, not walk, to the computer and put down an order for his Stockton bridge. I don't know how he makes any money selling these things. You're going to need meters, but these things are just remarkably sensitive. 2 watts on 30 meters pins a 1 milliamp meter. The insertion loss was 0.33 dB, perfect null when connected to a 50 ohm load. I mean, the meter was just laying on the peg. And the kit, I think, is, I don't know, 12 bucks, 20 bucks from W8DIZ. So I would go right now. Well, as soon as this is done, go buy one. If you're out there, W8DIZ, you can give me a commission. These are wonderful bridges. There it is. It works so much better with the 1N34 diodes than the recommended diodes. So, and you might be able to could vary the windings to lower the insertion loss. I surely wouldn't. 0.33 dB insertion loss, I wouldn't worry about it. The other thing is his bridge does not come with meters. but I would go on the eBay. There's a lot of people badmouth the meters from Chinese vendors, but I've gotten some really nice 50 microamp meters from Chinese vendors, and they work just fine. The W7 QRP watt meter is exquisitely sensitive and maybe really not designed for total inline operation. And it has a perfect null. The insertion loss was 0.6 dB. I remind people what Mr. Bell said about dBs, that 1 dB was the least detectable amount that the human ear could detect. So there you go. The cores that he built, his with the type 72 cores are no longer available. I use type 77 cores. That watt meter is exquisitely sensitive. I had no way of cranking the power down in that thing, but it probably works well down into the milliwatt range. And there's my version of it. The top one is the microstrip line, and then the bottom are the components of that. The bridge that I have in my shack that I use right now is pretty slick. It's if you Google G3YNH, you'll get this bridge. It requires some rather tricky components. There's some 3.3 puff capacitors and 70 puff capacitors. I happen to have a ton of NP0 capacitors, and I was able to find those values in there. And it is a dual sampling network. I built 3 versions of it. One has an insertion loss so low that it's considered basically not measurable. It's perfect low. They're not very sensitive. If you're going to build one of these, you really need a microamp meter. The one I'm using in my shack here is a 100 microamp meter. I could probably use a 50 microamp meter. And I found that the 1N34 diodes, it worked really well with the electrostatic shield version. And there's what it looked like. So I basically put it in a little box like this. You know, when you got tons of printed circuit board, you can just make these little things. And I use a heavy duty paper cutter to trim my circuit board. Here's another version of one of these things, one of the test versions. These are really fun to build. And you know, one of the nice parts about playing with antenna couplers is it's not just the antenna couplers you get to tinker with, it's all the ancillary devices, these bridges and all these other things. Those of you of us who go back far enough to remember when the micromatch and some of these early bridges came out, they're easy to build. You could build one in an afternoon. Now I'm compelled to talk about the vector network analyzer. I built a antenna for 160 meters in my backyard. I talk about it a little bit in a recent QRP quarterly article where I talk about my remotely switched antenna. 165 feet is a length that will give you 50 ohms resistive impedance on 160 meters, but with a considerable amount of inductive reactance. So you have to put a series capacitor in the line to tune out the reactance. My inverted L, by the way, goes up 75 feet and out 90 feet. It's pretty nice. Right now I got 47 radials in the ground under it. So the question I had was, could I use the nano vector network analyzer to measure the antenna impedance, and then just use an online calculator to come up with the appropriate L and C matching components? And I thought, because the online calculators are just wonderful. I mean, I can't even imagine going with a calculator and hacking my way through some of the old calculations. So let's go back for a minute and revisit my 22 kilowatt AM broadcast station. The daytime measurements of the inverted L antenna fluctuated severely. And it was my buddy VK6GX who suggested the problem was overload from the broadcast station. And sure enough, I think they go down their nighttime powers like 25 watts. So I went out there one night fighting the mosquitoes at 9 o'clock at night and set up with the vector network analyzer, and I got some pretty good readings, or what I thought were pretty good readings from the vector network analyzer. The nighttime power was reduced. So I was able to measure the feed impedance of the antenna. I also was able to measure the feed impedance of the antenna by hooking up an antenna coupler to it and measuring the inductance and capacitance of my 2 network antenna coupler. And I wanted to compare them to see how accurate the nano VNA was. And here's my little setup out in the yard. got a car battery. I got my AADE L and C measuring device. I got that other antenna coupler. I got my K2. There's a big car battery. And so I would just fire the rig up, tune this antenna for, and balance didn't matter here because this was an unbalanced antenna. Tune the antenna for no reflected power, and then measure the inductor value and the capacitor value. Well, if the nano VNA did its job, and the calculator did, they should pretty much be equal. Well, they weren't, and I thought, isn't that odd? So I decided I was going to build two little mini antenna couplers, one using the values from my L network coupler, just mimic those values, and the other one using the online calculator to come up with the values for the impedance of the vector network analyzer. And it turns out the nano VNA measurements were close, but the LC component values taken from the coupler were spot on. So I think the nano VNA probably works a lot better when you've got something that you're looking at with a piece of coax. I've fooled around with the nano VNA in the shack, and I found that the nano VNA, using it as an SWR bridge, hooking it ahead, basically looking at the output of the antenna coupler, it's more accurate than any of my bridges. So if you're gonna go out and try to replicate something like that, I don't think the nano VNA is the way to go. You might get close, I don't know. And so this is the antenna I was talking about, wireless control. And when I first put this together, it didn't work. And then I realized that all those inductors were wired on the wrong side of the capacitors. So this picture of the thing shows the incorrect thing. This is the article that showed up in QRP Quarterly. I got to pick up my little wireless device here. So I don't know what band my antenna coupler is set at right now, but one of the things I can do to reset all these relays to 0, I can just shut the power to my bias T, and then I turn the power back on. And what I'm going to do now is I'm going to switch this. Okay, my K2 is set for 30 meters. I'm going to push the 30 meter button. Boop. And the K2, I'm going to key it. Zero reflected power. This is pretty neat. So I have 6 relays here. One relay is straight through. I just take that wire and I send it down to my basement. I have a station down there that I listen to aircraft beacons. Position number 2 is the 160 meter band, and what that does is it puts a series capacitor in the line, and then the other circuits are 80, 40, 30, and 20, and they all have little L network components in there. What a nice thing to do. You know, this thing works. I was looking for remote control of an antenna coupler, and the expense that you could spend some real money doing remote control of this thing. This thing was about $30 for the combination. It gives me 2 transmitters, and it gave me 6 of these little receivers. The receivers are only single pole, single throw. So what the receivers do is they end up providing energy to the little relays. You can see the little dark smudges that are mounted on the opposite side, on the underneath side of that plexiglass board. And so this is really cool. Now, for those of you who are looking for an antenna coupler that, you just push a button and it auto tunes your antenna, this is not that coupler. This does not work like that. This is a fixed device for us, for an antenna that's out in my yard, and it's probably not going to, until that tree falls down, this is probably going to stay the way it is. And lastly, I think one of the better reasons to build an antenna coupler is to build it in memory of Lou McCoy, who must have written, got to be hundreds of articles about antenna couplers for the ARRL. What a great man, what great articles. And there's I think a book out there, it's still on eBay, and I'm going to see if I can't buy it one of these days. And lastly, the ultimate disclaimer, your mileage may vary. Imagine if when you were getting married, I now pronounce you man and wife, and he turns to your wife and says, your mileage may vary.